You think you know how rockets come back to Earth? Let me stop you right there. If your mind immediately pictures a giant, billowing parachute gently lowering a massive rocket booster back to the ground, dramatic descent through thick clouds, landing legs visible, parachute myth marked, that's not how the future works. That's not how we conquer the cosmos. The idea of a delicate piece of fabric saving a multi-ton metal cylinder that just blazed through the atmosphere is a beautiful but impractical fantasy. The forces involved, the sheer speed and heat, would shred a parachute into confetti. It's a relic from a bygone era when everything that went up was disposable. So, if it's not parachutes, what is it? Magic? Alien technology? No, it's something far more magnificent. It's science, it's engineering, it's the raw, untamed power of physics. A skyscraper-sized vehicle falling from the edge of space at hypersonic speeds. It then slows itself down. It steers with incredible precision. It lands upright on a tiny target, ready to fly again. A breathtaking ballet of technology, and will pull back the curtain on every step. Forget what you thought you knew. This isn't about gently floating down, it's about mastering a controlled fall, fighting gravity, wrestling with atmospheric drag, using fire to break against a planet's pull. A spectacle of controlled violence driven by mathematics and computer science. We're not just dropping things from the sky. We are teaching rockets to fly backward, to think for themselves, to land with the grace of a celestial acrobat. Before we dive into the nitty-gritty, let's just pause and appreciate the cosmic significance of what we're talking about. For the first 60 years of the space age, rockets were the ultimate one-and-done technology. Imagine building a brand new Boeing 747 flying it once from New York to Los Angeles, and then just pushing it into the Pacific Ocean. That's exactly what we did with rockets. We built these magnificent, complex machines, the most powerful vehicles ever created by humanity, and used them for a single, fiery, 8-minute blaze of glory before they became multi-million-dollar pieces of space junk. It was an incredibly expensive and wasteful way to explore the final frontier. This is why reusable rockets are not just an upgrade, they are a revolution. They represent a fundamental paradigm shift in our relationship with space. By making the most expensive part of the rocket, the first stage booster, reusable, we dramatically slash the cost of getting to orbit. Think about it. When access to space becomes 10 or even 100 times cheaper, what happens? The barrier to entry plummets. Massive satellite constellations providing global internet, large-scale space tourism, permanent bases on the Moon and Mars. This is the key that unlocks the solar system. This isn't just about saving money, though. It's about changing our entire mindset. It's about transforming space from a place we visit into a place we can access, operate in, and eventually live. It's the difference between a one-off expedition and building a reliable highway to the stars. The ability to land a rocket booster is the foundational technology for making humanity a truly multi-planetary species. It's the hello world moment for a new era of exploration. So if you're as excited as I am about what this means for our future, go ahead and double tap this screen right now. Let's feel that collective energy as we explore this incredible achievement together. What you're about to learn are the 3 core breakthroughs that cracked the code: the physics, the engineering, the onboard intelligence. We'll look at the flip maneuver that turns the rocket around the grid fins that steer it through the atmosphere like a futuristic skydiver, and the final nail-biting hover-slam landing burn. Our story begins at the very edge of space. The rocket's first stage has just done its job. Pushing the second stage and its precious payload, satellites, perhaps even astronaut stage separation occurs. The second stage continues its journey to orbit, but our booster is now a massive empty tube, traveling at several times the speed of sound and about to begin its long fall back to Earth. Its first challenge? It's flying backward and upside down. To have any chance of landing, it needs to completely reorient itself for a controlled descent. This is where the first piece of magic happens, the flip maneuver. Imagine throwing a pencil high into the air. For most of its arc, it's just tumbling chaotically. Now imagine that pencil could, at the peak of its arc, fire tiny thrusters to stop its tumble and point its eraser end perfectly back toward your hand. That's essentially what the rocket booster does. It uses small, cold gas thrusters, jets of pressurized nitrogen to push and nudge itself around in the near vacuum of space. With no air to push against, these thrusters are all it has. The onboard flight computer performs a series of precise calculations and fires these thrusters in short bursts. Now that our booster is heading back to Earth, it faces its next challenge: steering. It's falling from over 100 kilometers and needs to aim for a tiny landing pad. So how do you steer at supersonic speeds? You can't use wings. The answer is grid fins. These lattice-like structures act like 4 rudders in supersonic airflow. By changing their angle, the onboard computer can manipulate aerodynamic forces with surgical precision, steering the booster to its target. Our booster is screaming toward its landing pad at hundreds of miles per hour. This is where the most spectacular part of the process happens: the landing burn, often called the hover slam. It's an all-or-nothing, perfectly timed blast of power to kill the rocket's velocity in the blink of an eye. With only enough fuel for one short burn, the flight computer must calculate the perfect moment to ignite the engine. Ignite too early, and it runs out of fuel. Too late, and it won't have time to slow down. We've talked about the hardware, the thrusters, the grid fins, the engines. But what is the ghost in the machine that makes all of this work together in a symphony of controlled chaos? The true hero of the rocket landing is not made of metal, but of code. It's the Advanced Autonomous Flight Control System. This is the rocket's brain, a sophisticated suite of computers and software responsible for every decision from the moment of stage separation until the moment the landing legs make contact with the pad. There's no pilot with a joystick on the ground. The rocket is truly flying itself. Think of this system as the ultimate multitasking genius. It's constantly taking in information from a whole host of sensors. GPS receivers tell it where it is in the world. Inertial measurement units, or IMUs, which are kind of like the inner ear of the rocket, tell it which way it's oriented and how fast it's spinning. Barometric altimeters tell it how high it is. Radar altimeters tell it how fast it's falling. The computer takes all of this data, thousands of times per second, and compares it to the pre-programmed perfect landing trajectory. It then calculates the difference between where it is and where it should be. So the rocket has performed its hover slam, the engine has cut off, and for a brief, silent moment, it stands tall. Success. But where exactly has it landed? The choice of landing location is another critical part of the mission's design. Depending on the mission's requirements, specifically how much fuel the booster has left, it will either land back on solid ground near the launch site or on a specialized autonomous drone ship hundreds of miles downrange. This choice is all about energy management and physics. For missions that don't need extreme speed or a very heavy payload to a high orbit, the booster usually has enough leftover fuel for a boost-back burn. After the flip maneuver, it fires its engines to reverse course and fly back toward the launch site. It then performs a re-entry burn and a landing burn to touch down on a concrete pad. That maneuver is called a return to launch site, RTLS. It's the most fuel-intensive profile, but it makes recovery logistics far simpler. No fleet of ships required. For more demanding missions like sending heavy comm satellites to GEO, why teach a rocket to land? The answer is profound. It fundamentally changes our future. This technology is a quantum leap, redefining the economics of space travel. The most immediate impact is creating massive satellite mega-constellations. By drastically reducing launch costs, We can deploy thousands of satellites for a global high-speed internet network. It's a revolution in global communications, only possible because of reusability. Share this with someone who needs to see this. So, there you have it. The myth of the parachute is busted. The reality is a breathtaking high-tech dance of physics and fire, the elegant flip in the vacuum of space, precise steering with glowing grid fins, the final heart-stopping hover slam burn. We've seen how human ingenuity has tamed the beast of orbital mechanics. We have taught our tallest machines to fly home. This isn't science fiction. This is the world we live in now. The path to the stars is being paved, one incredible landing at a time. The sky is no longer the limit. It's just the beginning. This technology is a powerful reminder that the seemingly impossible can be achieved. It's a beacon of optimism, bold thinking, relentless problem-solving, a deep understanding of the laws of nature. This isn't just for a handful of scientists and engineers. This is a human achievement. Save this for later to revisit the magic of a rocket that knows its way home. Keep looking up. The cosmos awaits. Cosmos.